In this video, we'll discuss how to construct and interpret confidence intervals. But first, let's remind ourselves why we care. To this end, suppose we're interested in some population feature beta. For example, beta might be a model coefficient, a mean, or any other feature of the population. If we don't have access to data on the entire population, we can instead collect some sample data and estimate beta by beta hat, the corresponding sample feature. When interpreting and reporting this estimate of beta, it's important to consider the potential error in our estimate. To this end, we can construct a confidence interval for beta. This reports our sample estimate beta hat plus or minus some margin of error. The resulting interval reflects the potential error in beta hat while providing a range of plausible values for the actual beta, as opposed to reporting just our one best guess, beta hat, which is almost surely wrong. The central limit theorem, or CLT, provides one possible tool for constructing confidence intervals. Recall that the CLT assumes that the sampling distribution of the possible sample estimates beta hat is normal. Specifically, though different samples can produce different estimates beta hat, we can assume that these estimates are normally distributed around the actual beta value. Combining this result with the 68, 95, 99.7 rule for normal models, we can assume that 68% of samples will produce estimates that are within one standard error of the actual population feature. 95% will produce estimates that are within two standard errors, and 99.7% of samples, or nearly all samples, will produce estimates that are within three standard errors. In reality, we don't know the population feature beta. That's the whole point of confidence interval. It also means that we don't know where our estimate beta hat falls upon this scale, right? Our estimate might be above the truth, below the truth, close to beta, or far from beta. Yet, the CLT provides some assurances. Mainly, flipping the script, we can say that there's a 68% chance that our sample estimate is within one standard error of the actual population feature. Similarly, for the 95% and 99.7% levels. Thus, the central limit theorem provides a simple approximation for constructing confidence intervals at the 68, 95, and 99.7% confidence levels. A 68% confidence interval for beta can be calculated by our estimate beta hat plus or minus one standard error. For a 95% confidence interval, plus or minus two standard errors, and for a 99.7% confidence interval, plus or minus three standard errors. Please keep in mind that these are handy but rough approximations. We can calculate more exact confidence intervals at these and other confidence levels, not just 68, 95, 99.7, in RStudio. Further, given the randomness of working with data, sometimes our confidence interval is successful and sometimes it's not. For example, suppose our sample estimate beta hat happens to be just under two standard errors from the actual population value, beta. So here our estimate is marked by the red dot. Then our 95% confidence interval, calculated by this estimate plus or minus two standard errors, does include beta in the range of plausible values. This is good. In contrast, suppose we get an unlucky sample, which produces an estimate beta hat that's more than two standard errors from beta. In this case, our 95% confidence interval does not include beta. Thus, our conclusions will miss the mark. This is not good. It's important to remind ourselves that, in practice, we don't actually know the population beta value. Thus, we can't know whether our sample is one of the lucky or one of the unlucky ones. However, what we can do is choose our confidence level according to how certain we want to be about our confidence interval, including beta. This picture here illustrates some general themes. In a hypothetical, suppose that 100 different researchers each take a sample of size n. Then, each researcher uses their sample data to calculate a confidence interval for some population feature beta. Focusing first on the 95% confidence interval, notice that the point estimates of beta, or the beta hats, marked by the dots here, vary from researcher to researcher. Some are closer to beta, some are further away. Some are above beta and some are below. Accordingly, the 95% confidence intervals, which are centered at these beta hat estimates, also vary. Yet, among the 100 researchers, notice that roughly, though not exactly, 95% end up with a 95% confidence interval which covers beta. The unlucky confidence intervals, based on estimates that were just too far away from beta, are marked in red. Now, if the researchers decrease their confidence levels from 95 to 68%, notice that two things happen. First, the confidence intervals become narrower. In general, narrow confidence intervals can be good, since they help us focus in on a smaller range of plausible beta values. Yet, this also comes at a great cost. In making the confidence intervals narrower, or lowering our confidence level, we take on a much larger error rate. Notice that only roughly 68% of these 68% confidence intervals cover beta. Finally, if we swing in the other direction and increase our confidence level to 99.7%, nearly all confidence intervals will cover beta. This is good, but it also comes at a cost. The confidence intervals become very wide. To understand why wide confidence intervals aren't useful, consider an example. Suppose that with 99.7% confidence, a pollster claims that the president's approval rating is somewhere between 10% and 90%. And with 100% confidence, they claim that the approval rating is somewhere between, say, 0% and 100%. Now, it's great that the pollster is so confident in their statements, yet neither of these ranges are very helpful. A range from 10 to 90, let alone 0 to 100, is so wide that it tells us very, very little about the president's approval rating. With this in mind, depending upon the contextual consequences of making an error, we're typically willing to take on a little extra possible error in order to narrow our confidence intervals to a more meaningful scale. In conclusion, we've observed the following properties of confidence intervals. The higher the confidence level we use, the more likely the confidence interval is to cover beta. But the wider, hence potentially less useful, the confidence interval becomes. Further, though not yet explicitly stated, we've learned how to interpret confidence intervals. The easiest way to interpret a 95% confidence interval for beta is to say, we're 95% confident that beta is between the lower and upper bounds of this interval. Yet saying we're 95% confident is a bit vague, and we can be more specific. Specifically, we can say that there's a 95% chance that our sample produced a 95% confidence interval that covers beta, and a 5% chance that our sample happens to be one of the unlucky ones. This interpretation centers on the fact that the randomness in the confidence interval outcomes lies in our sample data. Though it's quite a subtle difference, we cannot say that there's a 95% chance that beta is in the 95% confidence interval. It's our sample data that's random, not beta. Thus, technically, beta is either in the confidence interval or it's not. So that probability is simply 1 or 0.